Welcome everyone. Again, welcome everyone to the IEP seminar this morning. We're receiving Paul Mollière, who had his bachelor degrees in the University of Heidelberg in Germany, and he did his master's in Cambridge, and then he went back to do his PhD in astronomy in Heidelberg again. Then he is now a postdoc researcher at his home institute, Heidelberg. And he, as I understand, he will probably be soon a staff scientist there. His main scientific interests are on the modeling of planetary atmospheres, where he has a very interesting code that's widely used by the community, especially the community in France. So I think he will tell us more about his work. So I'll give you the floor, Paul. Thank you very much. Welcome.
Yes, thanks a lot. Thanks for having me. I'm really looking forward to presenting my work here. So I'll first start the screen sharing, and now you'll see a weird subsection, but I guess it's looking good now, right?
Yes, it looks good.
Okay, cool. So, okay, thank you. Thanks again for having me. So I want to talk a bit about my research today, which is basically on measuring and interpreting the abundances of exoplanet atmospheres. And I'm listing a few of my recent collaborators here. I guess I could put more people on this list, but anyways, these are the people that I want to highlight here at the moment. So I want to start quite broadly with an introduction to exoplanets. So if you have never looked at one of these plots, if you're not an exoplanet researcher, this is actually kind of what the population of exoplanets look like that we know nowadays. So what's shown here is planetary radii of known exoplanets plotted against their orbital period. And if you don't know how we actually measure planetary radii, this here is a schematic of this. So a planet is, if we are lucky from our vantage point, transiting its host star, and the star becomes dimmer, and then we can measure the relative radius of the planet in comparison to its star. And a very famous instrument that detected many planets using this method was the Kepler Space Telescope. And so this is really basically as rough as you can get, just looking at the detected planets that we have in the most fundamental properties, such as radius, orbital period. And just by looking at this plot, you can already draw some interesting conclusions about planet formation potentially. So you could see, oh, there's a pileup here of planets which are larger than Jupiter, gas giant planets, and very strongly irradiated because they are in orbits of days basically around their star. And while it's true that these planets are basically the easiest to detect, even if you account for that, it's still true that this is an overdensity of planets. So planet formation must somehow lead to the formation of these planets that we have none of in the solar system, right? So we have Jupiter, but this is at 5.2 AU and not at 0.02 AU, basically. And there's another interesting pileup of planets. These are actually a bit unfavored to be discovered because they are smaller. So these are in size between Earth and Neptune size, so-called super Earths or mini Neptunes. And actually a lot of them, and any good formation, and I also want to point out again, we don't have such a system, such a planet in our solar system. Any good formation model should also explain how these planets form, basically. One can use another fundamental property of these planets, and this is the planetary mass. How is that actually measured? This is just using that planet and star are orbiting their common center of gravity. So then one can look at the stellar lines, and due to the Doppler shift, these lines will move back and forth, and this can be measured, and then we can back out what the planetary mass is basically. And then we actually have two measurements for a given planet if we are lucky, radius and mass. And we can use that to infer the density of the planet. And this could also tell us something about the internal makeup of the planet, which is again determined by formation, obviously. We can also basically look at other properties of the detected planets to learn something about formation. For example, we can look at the frequency of planets as a function of the metallicity of their host stars. So this is a very famous result by Fisher and Valenti from 2005. They've actually found that the frequencies of stars with giant planets goes up if the metallicity of the star increases. So somehow more metal-rich stars, and maybe by extension more metal-rich protoplanetary disks, are giving rise to giant planets more easily, which is actually an expected result if you think about core accretion, the core accretion paradigm of planet formation. You can do a bit more complicated analysis as well, using the masses of exoplanets and their radii. You can basically, as I said, you can constrain the density from this, and then using evolutionary models for the planetary interior, how the planet contracts over time, you can compare the current planetary density to what is expected actually at the system age, and look at that as a function of the metallicity of the planet. The more metal-rich a planet is, the smaller it will be in general for a given time. And this has been done by Daniel Thorngren in 2016. And a very striking result from the study is that as the mass of a planet increases, the planetary metallicity seems to decrease. So smaller or less massive planets seem to be more metal-rich, relatively speaking, than massive planets, which is a very interesting finding. And again, this is something that is kind of expected or reproducible using, for example, the core accretion paradigm for planet formation. So this is kind of cool, but these are all really conclusions that we draw from the really fundamental properties of these planets: mass, radius, occurrence rates, solar metallicities. And the question is, can we do better than this? Can we find anything out in excess of this? And a very powerful idea that was discussed first, at least for the exoplanet field, by Karen Urberg in 2011, is that we could potentially use the carbon to oxygen number ratio of exoplanets to say something about formation. And why is that? So what's shown here actually is the carbon to oxygen number ratio in a protoplanetary disk as a function of distance in the gas phase. This is in solid lines, and the solid phase in dashed lines. And what you see is, as you go further outside in the disk cools down in the midplane, becomes cooler, and then, for example, water starts condensing, CO2 starts condensing, CO starts condensing. And if that happens, that changes the carbon to oxygen number ratio in the solid or gas component in the disk accordingly. And now the idea is, if we measure the Cto ratio of a planet and also its metallicity, we can place the planet on this plot and kind of say where roughly in the disk it could have formed. And this is a very, very powerful idea, but I will also discuss later that it's very strongly simplified. Nonetheless, this has kind of sparked an increased interest of the community in the carbon to oxygen ratio and in general in exoplanet abundances as formation traces. And why do we actually hope how do we hope to actually measure the Cto ratio of planets? This is a very exaggerated example. So this is the emission spectra. These are the emission spectra of two hot Jupiter planets, so strongly irradiated gas giant planets. And one has a solar Cto ratio of 0.55, and one has a Cto ratio of roughly twice solar, 1.1 or so. And you see the spectra look completely different. And this is because the solar Cto ratio gives rise to water features, while the twice solar gives rise to methane features in this case. So in this case, obviously, it'd be very easy to say one planet is carbon poor in comparison to oxygen and one is carbon rich. This is a bit more nuanced, though, if you really look at the emission as a function of Cto ratio. This is shown here. So color-coded now on the y-axis. Color-coded now is the flux. On the y-axis, we have the Cto ratio, and still on the x-axis is wavelength. And you see there's a clear discontinuity. Basically, once the Cto ratio reaches a certain value, depending on the temperature of the planet, this can be around 0.7 or around 1. But then you have here methane-dominated atmospheres and water-dominated atmospheres below a certain Cto ratio. But even the smaller variations that you see here, these are still traceable with observations. So there's actually hope that we can measure the Cto ratio of planets. To be honest, though, with the state-of-the-art space-based instruments that we had until recently, JWST, Hubble Space Telescope, and Spitzer, these weren't really sensitive to the Cto ratio very well. So we couldn't use these very well to constrain the Cto ratios, basically just limits. And it's a bit changing at the moment that we can use ground-based instruments for doing that. But of course, the big thing on the horizon there will be James Webb and Ariel further in the future. But I want to first focus a bit on what we can do from the ground and have been doing from the ground recently. So one thing that we can do from the ground is—
Could I just ask a question, sorry, for the non-specialist?
Sure. Sure.
Can you just explain why the Cto ratio is important? I mean, it's not a biomarker or anything, is it?
I mean, that goes back to this Heidelberg plot that I was showing. Basically, the idea is in that very simple picture that if you know the carbon to oxygen number ratio, that you can potentially constrain where in the protoplanetary disk a planet formed. That's why that is of increased interest, or was of increased interest. It still is, and it's also potentially one of the more easier abundance ratios to measure in exoplanet atmospheres as well.
Okay, thanks.
Yeah, sure. Right. So talking about measuring Cto ratios from the ground. So one cool instrument that became available for this recently is the gravity instrument. So gravity is actually an interferometric spectrograph at the VLT that combines the light of the 4 UT telescopes of the VLT. And it's very good at, if you look at directly imaged planets, at disentangling the stellar photons at the location of the planet from the actually planetary photons. And the directly imaged planets that you can observe with this instrument, I show some of the poster childs here. This is, for example, HR 8799, the system of 4 planets, Beta Pig B, which is very famous, 51 Eridani, PDS 70. So if you look at these planets with gravity, what does the data actually look like? So what is shown here is the spectrum of HR 8799E. So black dashed is previous observations from the GPI instrument, which is a state-of-the-art single dish near-infrared telescope and spectrograph. And then you see in comparison, gravity does pretty well, especially close separation directly imaged planets. You see in gray dots what the gravity data looks like. And it's clear there's a big difference in terms of signal to noise and resolution. This is what gravity allows us doing. And this is, I think, 3 hours of observations with gravity. For Beta Pig B, it's a similar picture. Again, GPI is shown as orange dots, and then the K-band emission spectrum with gravity is shown as gray dots. Again, the signal to noise is higher and the resolution. And you can directly see by eye, like this is the carbon monoxide bandhead in that planet, and this is secondary bandhead here. So it's actually, becoming really obvious. There's carbon monoxide in there, and it's allowing us also, together with the water that's modulating the overall shape of the spectrum, to measure the carbon to oxygen number ratio on this planet. So having these 2 observations already, we then proposed for a large program. This was proposal was led by Sylvestre Lacour, and we actually got that accepted. So that's currently underway. This is called the X-Gravity program. I got in total, I think, something like 14 nights using all 40 UT telescopes together. So this gives us, of course, excellent K-band data for the dozen or so exoplanets that we can observe. And then the question now is, these observations, how do we analyze them? And this is where retrievals come into play. They are, retrievals is kind of like a glorified fitting, basically, and finding out what the properties of a planet are based on a spectrum that we observe. and that's what we call in the atmospheric community nowadays retrievals. So what do we do there? In my case, I use Petit Ratrans, which is a open source publicly available Python package that I wrote for calculating spectra and carrying out these retrievals. And it's able to also do scattering quite quickly, which is important because these planets are always expected to be cloudy, so you have to take scattering into account. And there are, of course, other codes that do that as well. To mention a few, there's Taurex, which is quite famous, Platon, Chimera, Nemesis. I'm sure I'm forgetting some, but that's the one that I wrote, so that's why I'm using that one. And this is then connected to a sampling tool, either Markov chain, Monte Carlo, or nested sampling. And this is basically what is fitting the observation, but also backing out the posterior distribution of the atmospheric parameters. So basically what's happening, to extend this a bit more, we have an observation called Y here. So this is this flux as a function of wavelength. And we have a model M. So this would be, in this case, Petit Ratrans, calculating the spectrum. And the input parameters theta are somehow parameterizing the atmospheric state, pressure temperature profile, cloud structure, abundance profile, and so on. And then Petit Ratrans does its thing and predicts a spectrum Y tilde. And then we calculate something like a chi-square, and then also take into account any prior knowledge that we have on the parameters. For example, like what do we expect the metallicity of the planet roughly to be, or we don't allow for negative temperatures. I mean, stuff like that. And then the sampling method, which is nested sampling here, basically fits the observation, but also backs out in the end the most likely parameters of the atmosphere given the observation. And we use PyMultinest for this, this nested sampling method. So what's gravity's view of beta peak B if we use a retrieval approach? This is shown here. In the upper panel, you have the archival GPy data that was in existence previously for this planet. And in the lower panel, we have the K-band spectrum of beta peak B. And you see in purple, that's basically a sample from the best. Basically, it's said like this. It's kind of the best fit model that we got from the retrieval. And you see it's fitting quite well, especially here where the signature noise is high. Of course, these data sets will dominate the fit, and we retrieve, can perfectly also reproduce this carbon monoxide bandhead and a bit of the secondary bandheads and the oval shape, which is dominated by water. And this fit had, I think, around 20 free parameters. And then you get like a 20-dimensional distribution of these parameters out given your observations, but then you kind of look at 2 and 1D projections of these parameters. And I'm showing you 2 interesting ones here. So one is the carbon to oxygen ratio that we retrieved, 0.43. And I want to mention we actually did a secondary analysis, second analysis in this paper. This was led by, in that paper by Benjamin Charnet using the XREM code, which is a more complicated, self-consistent, physically heavy code. And he found a very similar Cto ratio for this planet. So it's kind of also verifying our retrieval method here with a more complicated physical model. And this is what we found for the Cto ratio. What was also interesting, from the retrieval, we can constrain the gravity of the planet and also the radius, and we can use that to back out the mass of the planet. And this is what we got. And this is actually comparable with the astrometric mass that was known at the time, combining Gaia astrometry with Hipparcos. This was work by Ignace Sneller and Leiden. Since then, the mass has been revised to lower values, also using gravity astrometry and radial velocity data. So the agreement is less good, to be honest. But it's not too surprising to a degree, because log G is one of the more uncertain parameters that we back out from our methods. But of course, it would be nice if it was still agreeing as well as it did in the past. This is the retrieval for HR 799. that we carried out again in the upper panel. This is the archival data, and in the lower panel, this is the gravity spectra that we had. This is the 3-hour observation that was taken, and then in the background, these were like 15 minutes observations of the planet, which are more noisy because of that, but we still included them in this fit. And again, if we look at some of the retrieved parameters and the distributions and correlations between them, we see we get good constraints on Cto ratio, metallicity, log G, and radius. And these we actually compared to what was in existence as inferences for this planet from other methods, which did either more physically rigid, self-consistent grid fits to this data, or attempted some free retrieval as we did in the past, but with worse data basically. And what we found is actually that we agree where we have similar parameters that we retrieved. We agree quite well on the gravity of the planet, temperature is fine, but we were actually the first, also by virtue of the gravity data, to get a good constraint on the Cto ratio, which couldn't be constrained previously, and the metallicity, which is both important if one thinks about formation history potentially. We have since used the code on other targets. There was a paper on HD 206893b by Jens Kammerer. This was used to constrain Cto ratio metallicity, also in tandem with the Atmo retrieval code, where we got kind of consistent results on Cto ratio, but small differences also related to our model setup. I refer you to that paper if you want to know more. We're currently working on the paper for using the gravity data for all of the 4 H.R. 7 and 9 planets. So that's kind of this state of the art I would claim for directly imaged planets and retrievals at the moment. And this is the Cto ratio that's being retrieved here. I want to mention one cool other thing that one can do with these retrievals, and not only focusing on the Cto ratio. You can actually start looking also at isotope log detections and isotope ratios in wider separation exoplanets. So this was work led by Yapeng Zhang in Leiden. She's a PhD student there. And we looked at the SYNPHONY medium resolution spectrum of the planet TYC 8998760-1b. And this is what the data looks like. It was easier to observe with a single dish telescope because the orbital separation is just wider in terms of arc seconds. And you see here in white, that's the observation, and the fit is shown in red. And if you look at the residuals, you see they're quite small. There's maybe some accretion going on planets that we do not model in our retrieval. So that's why we have some larger retrievals somewhere. These I think are telluric sodium lines. But overall, we have a pretty good residual oscillating around 0. What's interesting though, we had 2 models that we tried, one including all the molecules of interest, and one basically leaving out 13 CO, so an isotope log of carbon monoxide. And you see actually exactly where the carbon monoxide bandheads are of 13 CO. The residuals become systematically larger if we do a fit in blue of a model that leaves out 13 CO. And we could actually show it. I mean, it looks a bit smallish here, but basically if you sum about over these differences, and you could also do a secondary analysis using a different method, we actually got like a 6 sigma detection for 13 CO from this data. So this was published in Nature earlier this year. And what was intriguing and a bit surprising is that the 13C to 12C isotope ratio that we found was about twice the local ISM value, I think at 2 or 3 sigma or something, which is pretty unexpected. At least if you think about this planet having formed like a star, just collapsing from the material, I don't know, in the protoplanetary disk. So maybe it formed differently. Maybe it formed by something like core accretion, where first you accrete a solid core and accrete lots of solids and then gassed later. And there was also like a hypothesis put forward in this study that maybe the planet formed outside the carbon monoxide ice line in the disk, where in the disk midplane, carbon monoxide was already condensed, but maybe not above the midplane. And there was a carbon isotope fractionation going on that increased 13 C content of the ice in the midplane. But that needs to be investigated further in the future. So to kind of also confirm that we can actually do this well and also get out expected, maybe more expected isotope ratios. So this was the first isotope log detection in an exoplanet ever. But we also, in a follow-up paper that Yapeng put out, have the first 13CO detection in brown dwarf so far, using a similar technique. Again, you see the residuals here when leaving out 13CO and then the 13CO model overlaid on top of that, and actually using the retrieval approach, but also using something called a cross-correlation method that sums the signal of individual 13CO lines. We got like a 8 sigma detection of 13CO in this case. And a bit more expected potentially. So this is a field brown dwarf. We got a 13 to 12C ratio that is more corresponding to the local ISM value, which is then more expected because we think that these objects potentially just form a direct collapse of gas in a giant molecular cloud or something. So that was just a short subtopic on isotope logs. Potentially there are more visible 13CO, but also other ones in the future for other exoplanets. So this is active research being done, especially in Leiden. But I now want to talk a bit about high resolution retrievals and the cross-correlation method that might lead to, or is already leading to good Cto ratio and abundance measurements from the ground, which is something that was not previously possible that well as well. So what is the cross-correlation method? I mentioned that already. So basically the cross-correlation is first of all just a mathematical, how do you say, a tool. So you basically, what does it actually do? You basically just multiply two functions and take their integral. And the cross-correlation has a variable, which is basically that you shift one of these functions by a certain amount in the x coordinate, basically. And now you can imagine these functions to be your observation, like a spectrum, flux as a function of wavelength. And you also have a model for the observation of the planet. And this is really at high resolution. So you have high resolution spectrum of the planet that has planetary lines in it. And you have a model for these lines on the planet. And then you just multiply them and take the integral. But what's important to know is that you have to know the actual velocity of the planet with respect to us really well to get a signal out basically from this cross-correlation technique. So the planet is moving, we are looking at high resolution, it has a systematic velocity with respect to Earth, it's going around a star, so there's like an orbital motion as well. So usually if you do this and you don't know what the velocity of the planet actually is, then there might be lines in the planetary spectrum. So this is shown with a strongly increased signal to noise here. So these white dots would be lines in a spectrum of a planet. And then you have a model that also has lines, but if you don't know the exact velocity shift of the planet, you multiply these two functions and you take the integral, you just get noise out basically. But if you find the correct shift, then these lines actually overlap. And then if you multiply these two functions and you calculate the integral, you get basically a increased integral value. And then when you compare the integral value for the good shift with the integral value of the bad shift, then you basically get like a signal to noise measurement out of this. And the powerful thing about this is that the signal to noise of this cross-correlation technique is actually equal to the single line signal to noise times the square root of the number of lines. And that's quite powerful because usually you don't really see single lines for an exoplanet. Maybe one line has a signal to noise of 0.5, 0.6, so you can't really detect a single line. But if you have 100 lines, your signal to noise of detecting a certain species all of a sudden is 6, so you can detect carbon monoxide, say, a signature noise of 6. And it's also quite unique potentially because these line positions for different molecules are quite unique. So it's more or less like a fingerprint analysis. Do I really see the lines of this species? What's nice as well, because of this Doppler shift, if you have a planet that's very close in around its star in its orbit, so it's orbiting very quickly during the observation, what will happen, for example, for hot Jupiter, if you look at an emission spectrum, so what's color-coded here is the emission flux, wavelength is here, and phase is on the y-axis, you see the planet actually going around the star. You see the Doppler shift. Again, this is basically infinitely high signature noise, so you'd never see these planetary lines normally. So you see the planet going around the star. You also see the waxing and waning of the planet, so the contrast between planet and star goes up when you see the day side of the planet. The cool thing is the lines of the star and the telluric lines will be stationary. So you can use that actually to reject the telluric contribution very well and the stellar contribution, and then you can isolate the planetary signal much better. And using this cross-correlation technique, it's actually also possible to run retrievals. So you can basically have a chi-square defined on the cross-correlation signal. And this is being done more and more nowadays. I want to highlight 2 recent papers, one by Peltier et al., where they did this for Tau B. This is a non-transiting hot Jupiter, and they could constrain the Cto ratio and metallicity. And also a recent one, Gandhi et al. 2019, again, where they could extract some constraints on the Cto ratio and metallicity. And this was not possible before from the ground because the data wasn't good enough. We didn't have these high resolution techniques, but with current state-of-the-art direct image planet observatories and also high-res, this is becoming possible from the ground. But now I want to talk a bit about, and obviously this part is less about my research already here, but also what's coming out now, because I want to talk a bit about James Webb now, which is not even launched. So what will James Webb be able to do on that front? How well can we measure abundances? So this is now talking or looking a bit on at transmission spectra of hot Jupiters. So again, transmission spectroscopy or transits in general is the planet blocking out part of the light when it's transiting in front of the stellar disk, and the flux decrease is basically proportional to the planetary radius, and the relative flux decrease is planetary radius over stellar radius squared. And what does that currently look like? We can basically make these measurements and look at the planetary radius as a function of wavelength. This is what that currently looks like if we use the Hubble Space Telescope and Spitzer. And why does that even change as a function of radius? Well, you can imagine that there's a certain molecule in the atmosphere that absorbs really well at a given wavelength. And then if the planet has an atmosphere with that molecule in it, the planet will appear bigger when it's transiting in front of its star. And this is what we are measuring. And if you look at the current state-of-the-art space-based data, you see it's actually, these are all different planets. Planet radius shown here. There's like an arbitrary offset to make it more visible. This is a plot from Singh et al. 2016. You see the data is often pretty noisy. Sometimes you can actually see quite well, like this bump here is a water absorption feature for some of the planets. Also for HG20 on 2948b, it's pretty obvious. But for some of the planets, it's actually just noisy, consistent with a flat line. Also, if you look more in the optical, we expect to see sodium, potassium features. Sometimes we see them, sometimes we don't. And also the slope here is sometimes much stronger than expected from Rayleigh scattering. So what's going on? So first of all, these observations are really challenging, and even HST is having a hard time, as you see. And also what's happening here is that clouds or hazes in these atmospheres are actually obscuring the molecular features that we expect to see. And that's a current issue with a lot of these observations, that we either don't see anything, or what we back out for the water abundance is kind of correlated with the cloud altitude in the atmosphere. So how will James Webb help with this? So these are predictions that I made in 2017 for what James Webb observations will look like. So what you see up here is a transmission spectrum measured with HST for a hot Jupiter called TRES-4b. So pretty noisy. And this is what one transit of JWST will give us. To be honest, these are actually 3 different transits in 3 different instruments of JWST. But basically here, this is one transit of JWST, this is one transit, and this is also one transit. And you see the signal to noise is much better, resolution is much better. And that's solving one part of the problem. But what's also the case, you see in the background here, these are models. The green one is a cloud-free model, where we clearly see molecular features in the near-infrared. But if you include clouds, actually, we lose a lot of these features as they become weaker. Excuse me. But if you look in the longer wavelength, near-infrared and mid-infrared, the clouds actually become less and less important. So JWST will not only have higher signal to noise, it will also probe wavelengths which are less affected by clouds. And this will help determining the abundances of these planets much, much better. What's also exciting, what you actually see here for this planet at 10 micron, these are actually resonance features of silicon clouds that pop up here. So this is the silicon oxygen stretching mode. And all of the clouds, usually they affect the near-infrared by just making that flatter, hard to see molecular features, but they don't leave any spectral imprint that informs us about the composition of the clouds. But actually with JWST at 10 micron, if it's silicon clouds, you can actually expect to see some features of these clouds. And for one transit, it looks a bit hard to see, but actually if you rebin strong enough, you can already see that there's more absorption here at 10 micron than you would expect if there wasn't any cloud. And yeah, it becomes visibly more clear if you do more transits, obviously. So that's kind of the cool thing about JWST for hot Jupiter planets. It would also do a great job for smaller planets, but I will not talk about this here. And just to show you a few of the predictions for JWST, this is work from Tom Green and my client from 2016 already. But actually, again, these are now retrieval results that ran synthetic retrievals for Jupiter. So these are emission spectrum retrievals, and you see here the white dashed lines are always what was put in, and you see depending on color coded here is which sub-instrument of JWST you use, we can constrain the Cto ratio pretty well for Jupiter's in emission, even if there's an inversion in the atmosphere. So the temperature gradient is like inverted. Depending on what instrument you use, you can still do a good job at backing out basically the abundances of these planets. It's a bit trickier if the planet is cloudy. Then potentially if you're unlucky, you get a biased result out for carbon oxygen number ratio. But still, in general, we expect to also get useful Cto ratio constraints, especially at the longer wavelengths, if you use JWST. Yeah, obviously, if you don't have clouds, it's easier to do that. So that's JWST. Something else I want to mention. So JWST will launch hopefully by the end of this year. Something else I want to mention is ARIEL. So ARIEL is an ESA mission that will hopefully fly by the end of this decade. And the cool thing about ARIEL is actually that it has different tiers that will look at roughly 1,000 planets that we can hope to get constraints on the abundances for, which is pretty exciting. And I think tier 1 has like 1 or 2 transits that it looks at per planet, and a lot of these are potentially a bit too noisy to get really good spectra out for some of these planets. For other ones, it might already be possible to get this quite well. But a point that they made in a paper from 2018 said even if you have lower res information for such planets, you can already start saying something about carbon oxygen number ratio trends if you have a lot of these, right? A lot of these measurements. So what they did here is that they took emission spectra in this case for hot Jupiters, synthetic ones, and basically rebinned ARIEL spectra to the classical Spitzer filters, Spitzer colors basically, and show that there's actually significant trends that you can expect to see as a function of the Cto ratio. So something like this, some kind of color analysis like this should become possible. It's already at tier 1, and there are tier 2, tier 3 parts of Ariel where there is a more detailed look that will be taken on planets that have a high expected signal to noise. And these are some predictions from this paper. I think this is HT 209, a famous hot Jupiter planet that they modeled here. And the dots are synthetic observations, and then the retrieval results for different Cto ratios are shown here. And again, this is the retrieval result. The Cto ratio should be well extractable from this. Okay, so I talked a lot about Cto ratios. I also want to mention a bit what we actually really hope to constrain with Cto ratios. I mean, I mentioned this Heidelberg plot already, and I want to basically talk about this a bit more realistically, what that actually means, not just looking at the Heidelberg plot and feeling happy about it. As I said, it's a very powerful idea and very influential paper, but that picture for sure is too simplified. So if we believe for a second that Heidelberg et al., their disk model was the truth, so what we can in principle do is take an exoplanet spectrum. So we run a retrieval, and we get a composition out, Cto ratio modellicity. And now we could imagine we now run a second retrieval, like a formation retrieval, where our observation is now the abundance that we inferred, carbon dioxide number ratio, modellicity, and so on. And then we have a fastish formation model. So we just take the Heidelberg disk, and we let a planet form at any location freely. It can accrete as much gas or solids as it wants from the disk. And the formation location and accreted mass are now free parameters. And this predicts also a composition, and we compare this to the measured composition of the atmosphere, and then we back out the formation parameters. And one can do that. Here's one example. If you do this for HR 8799E using the gravity constraints on the Cto ratio and modellicity. So what's shown here is the probability distribution of where the planet accreted its solids or where it sourced its solids from in the disk. So this is distance, and it just overplotted where the ice lines are. And we find that this planet most likely got its solids or accreted its solids outside of the carbon monoxide ice line. And the planet is nowadays further inside. So somehow it must have gotten from here to here. Maybe it accreted solids early and then migrated by disk migration, or it fully formed here and then disk-free migration brought it close in. Who knows? So we solved it, we can go home, everything's fine. That's not the case, unfortunately. And I just want to show you a few of the caveats that one has to think about when one actually really will attempt doing this. So what's shown here, again, is the carbon to oxygen number ratio as a function of distance in the disk. And if you look at the cyan lines, these are the static Heidelberg ice line Cto ratio changes that we have seen in these plots before. But now you can just include disk chemical evolution and let chemistry in the disk evolve as a function of time. And what's happening then is, for example, that carbon monoxide is in the outer parts of the disk in the gas phase is converted into carbon dioxide ice, and that essentially effectively moves the carbon monoxide ice line further in over time. And then if you run a formation retrieval as a function of time, what actually happens is that and this is basically a similar plot to the first one that I showed. So this is probability and where the solids are coming from for HR 8799. The cyan line again is the static Heidelberg picture, and the planet has formed outside the carbon monoxide ice line. But now if you include chemical time evolution, the planet has kind of formed further and further inside, and kind of, yeah, making our inference that we made on migration potentially invalid just by including chemical time evolution, which is most likely a very realistic assumption that this is happening. So what I want to say is that it's complicated. One thing that I mentioned is this chemical evolution. When doing that, you of course also have to know what is actually the stellar composition, what is the disk composition. Potentially these are the same or related. But it's also important, if you start a chemical evolution, you have to actually know, if I know the elemental disk composition, is that starting the evolution, and if the elements are in molecules, or are the molecules dissociated, and I start everything in the atomic phase. This makes a big difference when it's to know cosmic ray ionization rate, and these things are all important. So that all complicates this chemical evolution picture. Then also, if one wants to back out the formation history, most likely one will have to use a more complicated planet formation than what was assumed in these really simple formation retrievals that I showed. Not like a planet can form everywhere kind of model and create as much solids or gas as it wants to. There are concepts from planet formation that actually limit the amount of solids that could be created, something called the pebble isolation mass, the planetesimal isolation mass. Planets can migrate, they might be trapped at a certain location that's not fully free where they form. Planets can interact via n-body interactions that kind of randomize the whole process a bit. So these are all complications to be kept in mind. What's also important is there's actually no guarantee that what we see in the atmosphere is actually equal to the bulk atmosphere of the planet. And to elaborate this a bit more, this is work by Jérémy Leconte and Gilles Chabrier from 2012. And what they did actually is they said, well, let's assume we have Jupiter and Saturn, and there's a compositional gradient from formation, basically. There's maybe more metals close to the center of the planet and less at the top. Would we expect this to be fully mixed, that what we see in the atmosphere is indicative of the planet bulk composition? But what actually happens is what they found, that you don't start fully mixing the planet. You have something like a semi-convection behavior that develops because composition gradient stabilizes the planet against convection. And then you have kind of these metallicity steps in the planet and temperature steps. And you would not expect that the atmospheric composition is equal to the bulk planet enrichment. Maybe they're related, but they're not identical. It's also an important question if what you see in the atmosphere is actually equal to the bulk planet composition, because there could be comets or asteroids falling into the planet, especially if the system is still young and the planet is close in. Another complication to be kept in mind. And also, I guess we have to wonder about and test how reliable we can actually retrieve atmospheric abundances. I think this is a really sombering outlook, and you might wonder, why are we actually doing that then in the first place to measure abundances and hope to say something about formation? But I see this still a bit optimistic, to be honest. I just think this is not a thing that one solves during one postdoc. This is more like a maybe decades-long interdisciplinary effort of different branches of planet formation, atmospheric sciences. And maybe the results that we'll get are not as good or simple as what we hope to glean when we just look at the Urberg paper. Maybe it will be a bit more general and less detailed. Maybe we'll not get results for one specific planet, more for planetary populations. Something I want to mention as a positive outlook for the observational side is what kind of compositions we can actually measure already just for gas giant planets. So what I'm showing here are temperature conditions in hydrogen, helium-dominated atmospheres, so gas giant planets, over which we expect certain molecules to be present that allow us to measure the carbon to oxygen number ratio. This is water, methane, CO, CO2, C2H2. And this is all nice and well, but actually in the literature, there's more and more emphasis also being placed on nitrogen-bearing species. So HCN, for example, that traces, of course, kind of the carbon content, but also the nitrogen content of an atmosphere, depending on the temperature and Cto ratio, but also NH3 would be an important tracer. And it has actually been shown that N/H ratio might be a very useful ratio for tracing formation as well. And what I mentioned here as well, there's actually a vast array of species that trace the refractory content or rocky body enrichment of a planet. Some of these are already accessible nowadays with ground-based or space-based observations, such as sodium, potassium, metal oxides, metal hydrides, metal atoms and ions, with high-res observations for very hot exoplanets. But some of these also, like H2S, PH3, will be accessible with James Webb, also refractory clouds or gaseous silicon monoxide. And all of these kind of would measure the rocky body enrichment of a planet. So how much rocky material was accreted when compared to volatile ices or volatile gas. And this could also be a very powerful probe of formation. If you find a planet that has a very high rocky enrichment, then you could say, okay, it must have created lots of solid material and maybe less volatile ices. So maybe it formed quite close around the star, for example. So these kind of inferences will become possible. And with that, more positive outlook, I want to end this. And thank you for your attention. And I'm happy to answer any questions.
Okay, thank you, Paul, for this amazing talk. So we're opening for questions now. I don't see any hands raised yet. So I do have a question myself. You mentioned you are working on recent observations of HD 8799 from gravity.
Mm-hmm.
This is more like a technical question. In these gravity observations, do you get all the planets in one set of observations, or do you have to tune the instrument for each planet?
It's unfortunately not all of them at the same time, because gravity requires a fiber to be placed on the planetary location. So we have to know where the planet is, and then we can look at it. What's usually done for an average night basically is that one looks at HR 8799 and then cycles through the planets and spends like half an hour on B, half an hour on C, and so on, and for all of the planets. And that's also why you can't really use gravity for looking for planets and discovering them, because you would have to scan through
Okay, that's to know exactly where it is.
Yes. Yeah.
Okay, and still on that, on those observations, do you expect to? You mentioned the puzzle on the composition of the planet E, I guess, that you already measured. With the new planets, the new measurements, do you expect to have the same Cto ratio, or what's the?
I mean, I don't know what to expect. If you believed the Urbach picture for a second, and as I said, maybe that's not a good thing to do. We found that HR 8799E formed outside the carbon monoxide ice line. And that's actually the outermost ice line that's relevant for the Cto ratio. And at the same time, HR 8799E is the innermost of the 4 planets. So if then all of the planets formed outside the carbon monoxide ice line and they're all equally enriched in solids, my naive guess would be that they all have comparable Cto ratios. If the Urbach picture is I mean, I also have to be fair, I think. It was not Urbach's point, maybe that came across wrongly in my talk. It was not Urbach's point to solve it, it was just to put this idea out, right? But then people often think about the Urbach picture and run away with it and make certain statements about how the planet formed. But if the Urbach picture is not correct, I'm not sure what to expect, to be honest. There was a paper talking about disk self-shadowing, where at the water ice line, the disk is more puffed up and it casts a shadow behind it on the rest of the disk out to a certain radius. And then quite close to the star, the disk can cool down. And then carbon monoxide can actually condense much closer inside in the disk than what you'd normally expect for a simple disk model. And then we totally changed the outcome of where the planet formed based on the Cto ratio.
Okay, thanks. I have a question from Guillaume Lemebra.
Hello, Paul, can you hear me?
Yes.
Hello. I have a question about the results you present at the beginning about the gravity at VLT. With all the planetary systems that we know, which are directly imaged, and the ones that we can anticipate that will be detected in the future, with the current capabilities of gravity, typically how many systems you think could be characterized with the method that you presented?
It's like a dozen. So it's not that many. The reason for that is that these planets are actually quite rare, that's the most obvious reason, I think. Like early days when we didn't know yet, I think it was also partially the science case for GPI and Sphere. we kind of hoped that the planet occurrence rates could be extrapolated to outer radii, to where we expect these directly imaged planets. Unfortunately, that turned out not to be the case, and there are just not that many planets available that we can look at. So it's in the order of dozens, like 1 dozen planets that we are currently looking at. And Beta Pig B is the best one in terms of signal to noise because it's just really close. HRI 799 is like okay intermediate quality, but some of the other ones also give quite good spectra, and we are currently looking at these.
Okay, thank you. And thank you for your talk.
Thank you.
Okay, let's see, I don't see any more raised hand.
There's something in the chat, maybe. No questions.
Okay. Anyone else?
Okay, I'll stop the recording now. Thank you very much for your talk, Paul. And